China just unveiled a motor that claims 93.8% efficiency, but there's something unusual about that number. This isn't simply a more efficient motor, it's an entire electric powertrain compressed into one machine. So how did they do it? But what does 93.8% actually mean? Energy flows from the high voltage battery, through the power electronics into the electric motor, and through the gear reduction to the wheels. Every step introduces losses. Inverters lose energy during switching and conduction. Motors lose energy to heat through copper, iron, and magnetic resistance. Gearboxes introduce mechanical friction. Geely claims this integrated system developed with InfiMotion achieves 93.8% comprehensive efficiency under the CLTC cycle. However, this is a cycle-averaged calculation under laboratory conditions, not a claim that 93.8% of battery energy becomes wheel motion. The onboard charger is part of the architecture but remains inactive during driving tests. Shorter internal electrical paths reduce packaging losses, but undisclosed temperatures and battery conditions still boundary the claim. Standard electric vehicles distribute their core systems across the chassis. The electric motor, the inverter, and the reduction gearbox sit in separate physical housings. Nearby, the onboard charger, the DC to DC converter, and the power distribution unit require their own mounting brackets, distinct cooling ports, and dedicated heavy casings. This physical distance creates an immediate engineering penalty. Massive high-voltage cables and low-voltage wiring harnesses must snake through the car to connect these distributed systems. Every connection point, terminal, and casing adds electrical resistance, weight, and assembly steps. How do you combine these isolated components into one machine? How do you fit 16 separate systems into one machine? Geely and InfiMotion's answer is the Thunder Drive, an architecture that consolidates 12 physical hardware modules and 4 software control layers into a single, compact housing. First is the propulsion group, containing the permanent magnet electric motor, a reduction gearbox, and the silicon carbide inverter. Next is power conversion, combining the onboard charger and the DC to DC converter. Power distribution follows, integrating the power distribution unit, high voltage and low voltage battery management systems, active pre-charge control, and the power domain gateway. Finally, the physical package is completed by the vehicle control unit and an integrated thermal management system. But the 16-in-1 designation relies on an important engineering distinction. The remaining 4 features are not physical boxes at all. Instead, they are intelligent software control layers running on a unified processor. These layers manage real-time energy optimization, adaptive charging, dynamic motion control, and system diagnostics. By grouping these physical and digital systems on an 800-volt platform, Geely claims to eliminate more than 180 redundant components, structural casing walls, and internal connectors. What once required an entire engine bay of separate housings is transformed into a single cooperative system. How can something this compact produce 570 horsepower? Geely reports the entire Thunder assembly weighs just 75 kilograms, achieving an advertised power density of 11.8 kilowatts per kilogram. But there is an important distinction. That density represents a theoretical peak, separate from the 425 kilowatt combined output of the dual-motor production vehicle. Packing high-power silicon carbide inverters, an onboard charger, and a motor into one small housing creates severe physical conflicts. Thermal, electrical, and mechanical demands must be solved together rather than as separate problems. Bringing these systems closer concentrates heat, risks electromagnetic interference, and exposes sensitive electronics to intense gearbox vibrations. To manage these coupled loads, engineers designed a 54-channel directional cooling system, which Geely claims lowers peak motor temperatures by up to 15 degrees Celsius. In extreme integration, less hardware does not mean less engineering. Why does reducing wiring matter? In a conventional electric vehicle, separate modules demand a maze of heavy high-voltage cables and low-voltage harnesses snaking through the chassis. Every extra connector adds weight, assembly complexity, and contact resistance. By packing these components into a single housing, Geely claims a 30% reduction in high-voltage wiring and a 15% cut in low-voltage circuits. This translates directly to a lighter wiring harness, simpler assembly, and fewer physical failure points. Shorter paths potentially lower electrical losses, but compact wiring does not automatically yield a higher range. The real question is whether these condensed circuits can safely handle high-performance currents without overheating. The debut vehicle for the new powertrain is the Geely Galaxy TT, a sedan that serves as the primary testbed for these performance claims. Geely reports that this all-wheel drive vehicle produces a combined output of approximately 425 kilowatts, which is equivalent to about 570 horsepower. Rather than using a single large drive unit, the vehicle relies on a dual-motor configuration, pairing a 180 kilowatt unit on the front axle with a 245 kilowatt unit on the rear. Under peak load, Geely claims this setup accelerates the car from 0 to 100 kilometers per hour in approximately 3.8 seconds. This performance shows that high power and energy conservation can be compatible, even though they remain competing engineering demands. But acceleration is only one side of the ledger. The other is energy consumption. Geely reported an average consumption of just 8.20 kilowatt hours per 100 kilometers during a challenge around China's Qinghai Lake, securing a Guinness World Record. This controlled route result represents extreme potential rather than realistic everyday use. The test was conducted under highly specific conditions. Factors like vehicle speed, ambient temperature, flat terrain, and minimal wind were carefully selected. The team also optimized tire pressure, selected specific low-resistance tires, turned off auxiliary loads, and maximized regenerative braking settings to match a disciplined driving style. Changing any of these variables or the test procedure itself shifts the math. In daily use, factors like normal traffic, cold weather, high-speed driving, and active heating or air conditioning will raise consumption. The record proves what the hardware can do under perfect parameters, rather than what it delivers on a standard commute. Extreme integration changes how engineers design a vehicle. By eliminating more than 180 redundant components and packing the electronics into a single housing, Geely claims to free up packaging volume on the axle. For the Galaxy TT, this consolidation reportedly provides about 28 liters of extra front trunk space. It also simplifies manufacturing by requiring fewer physical mounting points and shorter electrical routes. When viewed as packaging efficiency, the reported 11.8 kilowatts per kilogram power density represents a direct drop in physical overhead. Shedding weight and freeing volume gives designers structural flexibility, translating to potential efficiency gains across the complete vehicle. But there's a catch. This extreme physical integration highlights the fundamental engineering tension of fewer components versus greater system complexity. Inside a shared enclosure, thermal management becomes a collective struggle, as multiple heat-producing domains must share a single congested coolant loop. If any internal component, like the DC to DC converter or the onboard charger, suffers a localized failure, isolation is physically impossible. Instead of swapping a single cheap module, owners might be forced to replace the entire drive unit. Diagnostic software must dynamically decide whether to isolate the fault or shut down the vehicle entirely. Without years of public field failure data, the real-world durability of this design remains an open question. Tesla popularized the 3-in-1 drive, merging the motor, inverter, and gearbox. BYD expanded this to 5-in-1 packages, while Xiaomi adopted 8-in-1 units. Global suppliers like Bosch and ZF offer similar unified architectures. This consolidation cuts weight and packaging overhead, but efficiency gains eventually plateau once dominant mechanical and electrical losses are reduced. Geely and InfiMotion's 16-in-1 claim escalates this competition. Could this become the standard architecture for future electric vehicles? The real step forward isn't simply making one motor more efficient, it's making an entire electric powertrain behave like one machine. And that could be where the next generation of electric cars gets smaller, lighter, and more efficient. Today, the race for EV supremacy is no longer won on paper specs, but deep inside the chassis. The ultimate challenge isn't building a better motor, but mastering extreme integration. As boundaries shrink, the future belongs to whoever manages complexity without sacrificing reliability. Join the conversation below.